fine.
Yeah. Let me go ahead and probably send a reminder to everyone.
Hello?
Hey, hi, Dr. Smolka. How are you?
Oh, 1 second. Sorry, I didn't have my volume turned up. Hello?
You're fine. You're fine. We can hear you.
Okay. And the video is okay?
Yeah, it's perfect. Thank you so much.
All right. I'll join you again in a few minutes.
Do you want to just go ahead and see if you're able to probably share your slides?
Okay. Just 1 second. I have to go back to Zoom. You've disabled screen sharing.
Okay, hold on. Okay, could you please, okay. All right, can you please check now?
Yeah,
I can see you. Awesome. So probably can we just go ahead and see if your slides work fine? Yep. Perfect. Wonderful.
let me get into presentation mode. Okay, is that?
All right, perfect.
All right, great. I'll talk to you in a few minutes. Thank you.
Yeah, thank you.
You're home, buddy. You a good boy, huh? Be a good boy. Yeah. Right.
Hey, dear everyone. Thank you so much for joining. I think let's start. So I would like to welcome, are you able to hear me, Dr. Smolka?
Yes, I can. Thank you.
Okay, wonderful. Thank you. Let me welcome Dr. Scott Smolka. Dr. Smolka is a Sunny Distinguished Professor of Computer Science at Stony Brook University and a Fellow of the European Association for Theoretical Computer Science. His research interests include model checking, runtime verification, and the modeling and analysis of cyber-physical systems, including cardiac tissue, neural circuits, and multi-agent flight information. He's the lead PI for the multi-institutional NSF CPS Frontiers project on cyber cardia, compositional, approximate, and quantitative reasoning for medical cyber-physical systems. He is perhaps best known for the algorithm he and Dr. Paris invented for deciding bisimulation. Dr. Smolka was jointly awarded the 2021 ACM Edsger Dijkstra Award for his work. Smolka's research has resulted in more than 200 publications, generating more than 10,000 citations. He has also been PI and co-PI on grants, totaling more than $30 million. And today, Dr. Smolka will be presenting on the topic, a bird's eye view of flocking. Welcome, Dr. Smolka. We are extremely excited to have you as a speaker today.
Oh, thank you so much for the kind introduction, Gokula. I appreciate it.
My pleasure.
Welcome to everyone. Yeah, as was mentioned, I'll be talking about the flocking problem. And let me just get started. So this is first, I want to say it's joint work with the following people: Usama Mehmood, Shovik, Radu Grosu, Scott Stoller, and Ashish Tawari from Microsoft Research. This is a special occasion for me to be able to give this talk to everyone here at Augusta University. I have close ties with my cat, who needs to get into the picture, with Alex, who we go back to around 1990 or somewhere around there, and both went to Brown University and were advised by Paris Kanalakis, which is a significant distinction that we both share. I know Paul also for a long time, and we actually wrote a paper together, I think it was in 2004, on interactive Turing machines. And Rich is a recent PhD graduate of mine, so who recently joined Augusta. So like I said, a special connection to Augusta University, and I'm happy and privileged to give this talk today. So here's an outline of the talk. Let me get right into it with the introduction. So, you know, I called the talk a bird's eye view. I actually have sort of at times a bird's eye view of flocking. So this is taken from an upstairs bedroom in my house overlooking the harbor in Port Jefferson, which is part of the Long Island Sound. And this is a flock of seagulls that was just out and about one day searching for food, probably. So the question is, why do birds flock? And there are a variety of reasons. You can see them listed here. So for foraging, it allows many birds to search for and take advantage of the same food supply. So that's certainly important. Protection, a larger group of birds has a better chance of spotting a predator. And also, as I'll show you a video of confusing or overwhelming a predator. Most of the flocks I'm considering really are starling flocks, and predators for them. One of the main predators is the peregrine falcon, which is a very capable predator. It can actually, when it does a dive into a flock, it can reach speeds up to 200 miles an hour. For mating purposes, the males can show off their breeding plumage to the females in the flock, making themselves more visible to a greater number of females, so increasing their chances of successful mating. Communal warmth is certainly a benefit, and from an aerodynamic point of view, collective flight formation among birds, such as the V formation, can lead to aerodynamic benefits. So the bottom line is that birds that stay together, or birds that flock together, tend to survive together. And please let me know if you have any questions. I'm happy to take them. Now, although I'll be talking about bird flocking and starlings and things like that, I'll also show you some experimental results involving drone hardware. This is ultimately our goal: autonomous systems. So as I mentioned, there is this case of what I call extreme flocking, or more commonly known as murmuration. And let me just run this short video to give you an idea of what a collective action of a flock can do to avoid and overwhelm and just put on an aerial display when it comes to predators and other observers. So this is taken near the Termini train station in Rome, Italy. And so there are researchers in Rome, led by Adanasi is her last name, who study flocking, and they take high-speed videos and analyze them frame by frame, and have come up with very interesting observations. And I'll rely on some of their work in my talk. Let's see if I can move past this one. Here we go. So back in 1987, Craig Reynolds came up with a dynamical model, a computational model, if you will, of what he considered flocking. And this was an extremely successful effort on his part. And he used it, it was used in Hollywood for animation effects, and it made him, made him a career actually in Hollywood. So what is Reynolds' model? It consists of 3 interaction rules, each of which produces a steering force that will tell you where an agent or a bird is going to go next in terms of in time and space, based on its interaction with its neighbors. So the agent in question that's following these rules is in green in the middle. You can see its green triangle represents its position. And then you can see also its, at least in this slide, its heading angle and acceleration. And so the alignment rule says that this agent in the middle steers towards the average heading of its nearby flock mates. You can see there's some interaction radius, and it looks at these flock mates and steers towards the average velocity of these agents. And so that's why you see a red force applied to the agent that moves its directional movement to the left, to more align with its neighbors. Cohesion is it steers towards the average position of nearby flock mates. So it wants to get close to its flock mates. And on the other hand, separation is sort of the opposite steering motion. It steers to avoid crowding from nearby flock mates, and you can see it steering away. So it's especially this combination and this balance between cohesion and separation that Reynolds discovered leads to flocking. So we'll, we certainly gained tremendous inspiration from Reynolds' flocking model, and you'll see how our work is related to Reynolds' work, but also different. Now, another early attempt or approach to flocking is the Olfati-Saber model, which is based on an artificial interaction between agents is modeled as an artificial potential field. And you can see that illustrated on the right. And the potential for a pair of agents has its minimum at the desired interagent distance d of the resulting alpha lattice. So it's an alpha lattice where agents are distance, try to be distance d apart from one another. So in agents acceleration, we saw how agents accelerate in Reynolds' model based on those 3 rules. In the Olfati-Saber model, their accelerations are based on the sum of the forces from all their neighbors and also a velocity alignment term. I'm not going to go into more detail, but so this potential is at a minimum when agents are d apart, which leads to this alpha lattice with interagent distance d. There are other alpha lattice-based approaches to flocking. There's centralized and distributed MPC approaches that are based on work by Zhang and Li. And I'm not going to get into too many of the details about MPC, which stands for Model Predictive Control right now, because I'll be talking about that later in our work. But the idea is that there's a cost function that agents have to collectively minimize, the cost function G that you can see spelled out here. And it's minimized when agents are exactly distance d apart. So this is another way to get an alpha lattice with distance d between agents. That's all I'm going to say about this for now. This is just background work. So let me get to our first contribution, which is what we call declarative flocking. And we're going to use optimal control to define flocking controllers, both in the centralized and distributed settings. And again, we'll have similar to what we saw before. We're going to have an associated cost function, and it will have terms for cohesion and separation, again inspired by Reynolds, but they will look a little bit different than what was in Reynolds' model and spelled out differently. So we're not going to have any hard-coded rules. We're just going to have this cost function that agents are trying to minimize. So it's a more declarative approach and less rule-based, of course. So the flocking controllers will seek to minimize the cost at every time step to generate their accelerations. So let me give you some details. First, this is a preliminary slide for declarative flocking. So this is just a very simple model dynamics slide. We have more sophisticated model dynamics that we consider later on. But for the purposes of illustrating declarative flocking, the state of an agent I, amongst n such agents, is given by its position in space x sub I and its velocity v sub I. And so a state of the collective is given by a set of n agents, xi and vi. And their discrete time equations of motion are just that an agent I moves to its next position in space based on its current velocity. And also its velocity is determined by its next velocity is determined by its current velocity and its current acceleration. And dt is the duration of a time step. So very, very simple rules, equations of motion, I should say, and there are bounds v bar and a bar respectively on an agent's velocity and acceleration. Now, this agent I's acceleration is in green as in contrast to everything else that's in red, because the acceleration a sub I at time t is provided by the flocking controller in our case. So it's an input to this agent. So the trick is, how do you provide the AIs in such a way that you collectively get flocking? And we have, as I said earlier, we're going to have a cost function that each agent is going to try to minimize. And by each agent doing this collectively, the goal is to achieve flocking. So again, we're inspired by Reynolds. We have a cohesion term where it's just based on the square of distances, interagent distances between agent I. This is the cost function for agent I, j sub I at time t. So this is the distance between agent I and its neighboring agent j. So we look at all of agent I's neighbors j at time t. And then you have, for separation, it's sort of the inverse of that, as you might expect. And again, for all of its neighbors, we look at the inverse of the distance squared between I and neighbor j. And both terms have an associated weight, omega sub c for cohesion and omega sub s for separation. And both terms are normalized by the by the size of agent I's neighborhood at time t. So this makes things easier to manipulate. So again, j sub I is a distributed cost function. We have the weights for the two terms. Euclidean distance between agents I and j is this double bar notation, as you would expect, and so forth and so on. Now, as I'll later show in this talk, the declarative flocking approach, the cost function can be easily extended with terms for obstacle avoidance, leader following, predator avoidance, and so forth and so on. And this is another illustration of why the approach is declarative and easily extendable. So how does model predictive control work? Because in our case, agents are going to use, each agent I is going to use model predictive control to figure out this next acceleration. And how are they going to do that? So to find a best acceleration a sub I at time t, that will be, in other words, one that will lead to a flock formation, the way model predictive control works, and maybe some of you are already familiar with this, and I hope I'm not stating the obvious, but anyway, so first of all, you have to develop a model of the plant. But we've already done that. I showed you the model before. So the model is used, that I showed you before, is used for simulation purposes and for MPC. And then at each time step, the agent is going to use the model and an optimization solver to determine the control inputs that minimize the cost function, J sub I, in our case, over a finite prediction horizon, capital T. So you'll look, the agent will look capital T time steps ahead and see what these accelerations do in terms of minimizing the cost function. And once you found that optimal sequence of accelerations, you apply the first of them as the control action to agent I's plant. And then you repeat at time t plus 1 after updating the model state with new plant measurements, assuming that you're running on real hardware and you're performing MPC in software on the hardware. In what I'm showing you here, there really isn't a distinction between the plant and the model because we're just doing simulation right now. Later on, that'll change. So as I said, you have to use the model and an optimization problem to solve this cost minimization problem. So what is the cost minimization problem? So at time t, we solve the following local optimization problem. So we want to find the optimal accelerations for agent I at these various time steps, starting as computed at time t, as predicted at time t. So we go from t to t plus capital T minus 1. Capital T, again, is the prediction horizon. And it's an argmin problem. We're finding these accelerations, and that will be assigned to the starred ones on the left, that minimize the sum of the cost function in our case at every time step in the prediction horizon. Again, prediction horizon is capital T in length. And these are the optimal accelerations for agent I at time t prime as computed at time t. And we can now set agent I's acceleration at time t to the first one computed in the prediction horizon. So AI star at time t as computed at time t, starting at time t. And that's how MPC works. Is really, I mean, there are variations on it. This is what we do, but this is basically how it works. And this works well for flocking, it turns out. Distributed flocking. You could also look at global flocking, where an agent's neighborhood is every agent, or you can just run this optimization problem over the entire collection. So I want to now show you how well declarative flocking performs, distributed declarative flocking. And to do that, we'll look at some performance measures, which are illustrated here. We'll look at the number of connected components. Here you see the number of connected components in this collection of agents is 3. Maximum diameter, you can see that's the largest distance between any two agents in the flock, or subflock as the case may be. So that's D. Irregularity is sort of the standard deviation of the interagent distance. Here you can see that the bold edges represent distances that are all the same. And so these are the regular edges. And then velocity convergence is for each subflock, as the case may be, how aligned their velocities are. So for all 4 of these performance measures, smaller values are better values. So in terms of getting optimal performance, we want to minimize the number of connected components, the diameter, irregularity, and velocity convergence, the way things are defined. So here is some snapshots of what we got running for 30 agents, running our approach, declarative flocking centralized and declarative flocking distributed. I briefly mentioned the centralized approach. And we compare it with so this is formations that we ran each of these different approaches that I've talked about, Reynolds and the alpha lattice. This is the MPC-based approach to the alpha lattice technique. This is a centralized case, this is a distributed case, and here's Olfati-Saber. So you can see that for the more natural flocking like behaviors, Reynolds and our two approaches, distributed and centralized, come out as the better alternatives. I think the emphasis on these alpha lattice-based approaches to enforce this interagent distance D can lead to fragmentation, and it can lead to some non-natural formations. So I'll say a little bit more about this as I now show you a few snapshots of our results. So this is a little bit complicated slide, but let me take you through it. Our approach is declarative flocking centralized in the red dashed line and declarative flocking distributed in the gold dashed line. And you have Reynolds is in green, I guess because he made out so well with his technique. And then you have the lattice approaches distributed and centralized, and Olfati-Saber in this kind of pinkish dotted behavior. So in terms of connected components, for Reynolds in green and our centralized and distributed declarative flocking approaches, they do the best. They minimize the number of connected components right around 1. Where it starts to go up, you can see that for lattice centralized and for Olfati-Saber, they go up to 6 and 8. So there's quite a difference in terms of number of connected components that we observed in simulation. And for the diameter, again, declarative flocking centralized and declarative flocking distributed do extremely well. Reynolds is not too far behind, and the alpha lattice-based approaches tend to have a much wider diameter, which is not what you want. In terms of interagent distances, again, basically all the approaches do pretty well at maintaining that interagent distance to the standard deviation of the interagent distance to being very low. Surprisingly, that's not the case for Reynolds model. This is the outlier for interagent distance. Velocity convergence, all of them actually do well. There's some disruption in that in the beginning, and that's because in the beginning of the simulations, because agents are starting off at semi-random positions in space. So they need to accelerate in different manners to get into a flock formation. But once they do, velocity convergence is demonstrated. So that's our declarative flocking results. What we decided to do, and please let me know if there are any questions. What we decided to do next is follow the trend, this is a couple of years ago, and see, can we devise a neural controller that exhibits flocking behavior. And so we took this approach. We're using supervised learning, and the centralized MPC controller for declarative flocking is providing the labeled training data to the learning agent, which you can see here. We call it a distributed neural controller, or DNC. And it's symmetric. We just learned one distributed neural controller, and then we can instantiate it as many times as we want because it's symmetric and get a flock from that. So I call it labeled training data because the training data is labeled by accelerations, which is what you're trying to teach the neural controller. So training data is of the form state, state, here's your neighbor's state, and here's your state, and then label, which is the corresponding acceleration that the distributed neural controller should learn to take. And then we evaluate it on various trajectories, as I'll show you. And we compare its performance to our distributed MPC controller, which I just showed you performs quite well. So it's up against a formidable competitor in distributed MPC. And not only will I show you that it performs well, but I will also show you that this approach generalizes quite well in terms of number of agents. So here are, again, some of the control objectives we trained for, and they're illustrated actually on snapshots of our distributed neural controller that we learned. So this is just evidence right up front that it did well. So here we see, I think there are 20 agents here, or 30, I forget. Yeah, I think this is 30. And each agent's position is represented by the red circle, and its velocity is represented by the blue edge coming out of the body of the circle. And so here you can see for basic flocking that the neural controller performs quite well. Looks like a flock to me. And in terms of obstacle avoidance, which I have videos, short videos for obstacle avoidance and predator avoidance, they do very well. This is the predator in black that is trying to head towards the centroid of the flock, and the flock does a great job of maneuvering around or avoiding the predator. And target seeking, this is where the agents converge upon a target location. And I think this is for 30, the snapshots are for 30 agents, which already demonstrates generalization because we trained the DNC, the distributed neural controller, on 15 agents worth of data. So the training data and the architecture for the DNN that we used is illustrated here. The inputs depend on what you want to do, what you want to train this neural controller to how to perform. Is its goal just to perform basic flocking? Then these are the inputs. Do you want it to perform basic flocking plus obstacle avoidance and target seeking? Then we have these additional inputs. So besides positions and velocities, you also have the location. This is for 15 agents, the location of the nearest obstacle to each agent. And for target seeking, you have the goal location is also provided as a training input. And then for predator avoidance, you want to always know where the predator is in space and time. So in this case, the training data is given by agent 0 in terms of its positions and velocities, and we always assume it's at position 0, 0, so that all the other agent positions are relative to the training agent. And the output, you can see we have some number of layers. We use a DNN with 5 hidden layers, each with 84 neurons, turned out to work well. And the outputs are, given these inputs, what state you're in, here is how the DNN should accelerate. Okay, so that's the basic layout for the neural flocking controller. And here's just some training parameters information. We sampled training data for 15 agents from some initial position distribution and initial velocity distribution. You see given here. The number of training samples was 200 trajectories worth of training samples times 1,000 time steps each, involving 15 agents. So that came out to about 3 million training samples, which proved quite sufficient. And batch size was 2,000, number of training epochs, 1,000. We used the ADAM optimizer, and the number of training parameters turned out to be almost 34,000 for basic flocking, and it was a few thousand higher for the other variations. And we ran Keras on top of TensorFlow for training. So here is just in terms of these same type of graphs I showed you before, just to illustrate the performance of the neural controller, DNC in red, versus DMPC, our declarative flocking for the distributed case and for the centralized case. And you can see that in terms of the diameter, it did very well. I mean, there's a little bit extra oscillation in the beginning, but then it quickly converges to the same, diameter as the other two approaches that we compared against. And the same thing for velocity convergence. So there's a few extra moments where velocity convergence hasn't taken place, but then it rapidly converges. So, but the main takeaway here, sort of the main takeaway, is that if we average over 100 runs, the execution times per time step, for centralized, we get this, 80.6, distributed, we get this, and DNC, our distributed neural controller, is 1.6 milliseconds per agent. So that means that our distributed neural controller is 36 times faster than the distributed MPC declarative flocking controller. And that is ultimately to have something that's high performing, and in terms of these performance metrics we've been evaluating, and high performing in terms of speed, you sort of get the best of both worlds, not to mention the generalization to more agents. So there's a question. So the neural net only learns the behavior of one agent. That's correct, but it is a symmetric controller. So it can be instantiated as many times as you want. Thank you for the question. So this is the bottom line. In terms of generalization, I have a slide about that. So we trained on 15, but we generalized to 40. And we showed that the convergence diameter, generalizes in ways that we would expect it to. The convergence rate in terms of reaching a flocking formation, it does start to degrade a little bit. After 30, it dips down to 35 agents, it dips down to an 86% convergence rate, and then 81 for 40. The convergence times progress in a way that we would expect. And the interagent collision rate, which you can see here, is very low, even up to 40 agents. We also looked at obstacle avoidance and predator avoidance. And from 15 to 40 agents, the neural controller did extremely well. Excuse me. So we're very pleased with these results. Let's see. So, okay, so then it applies that the behavior to each agent independently. That's right. Yes, thank you. So as I promised, I wanted to show for 30 agents the obstacle avoidance behavior video for the neural controller. It's instantiated 30 times. And it has to get around this obstacle field, and you can see it's very adept at doing that. And it actually reaches this target location and then swarms around the target location. And for predator avoidance, the predator starts here. The flock is here. I'll just run a short video again. The predator is faster and more agile, but still can't catch up to the flock as best it tries. So that ends my discussion of neural flocking. The next item I'd like to talk about is high-speed flocking maneuvers. Excuse me. So flocking maneuvers, which really mean, for the purposes of this talk, high-speed turning maneuvers, flock-wide turning maneuvers. So these flocking maneuvers are employed by starlings for a spontaneous change in travel direction. And this is something that flocks want to do, again, for predator avoidance and things like that. And they're usually initiated by a few individual birds, and a few individual birds decide, let's initiate a turn, and that will influence in a rapid process. It'll propagate rapidly throughout the flock that, hey, let's make a turn. So it's a very interesting phenomenon. And it's something, if you think about it, it's something you've seen in like a chorus line, where the chorus line members kick in sequence, kick their leg, right? And that's sort of, oh, this guy's kicking the leg, I better kick my leg, and so forth and so on. You also see it for those of you that are go to baseball games or whatever. You'll see a wave in a stadium, or in a soccer match in Europe, you'll see the wave through the stadium. It's kind of the same idea. And this propagation that you see in these situations, including turning maneuvers, follows a linear dispersion law. So it's basically a scale-free phenomenon. And in the case of starlings, again, Adanasi in Rome, by analyzing their high-speed videos that they took of these flocks and their turns, they found out that the initiators usually are at the tips of this elongated flock. The flock is usually elongated, it's wide, and at the tips of this elongated flock, those are usually where the initiators are located. And there's a couple of reasons why that's where you would find these turn initiators. One is that these initiators out on the tips are more susceptible to being eaten off or killed off by predators, because they're more vulnerable out there. And also they witness, or they are, I can't think of the right way of putting it, but they are not getting that much social interaction being out on the wingtips, right? So they lack social interaction, and they want to change their position for that reason as well. So that's another reason they might initiate a turn. So how do we take care of this in terms of our declarative flocking scenario? Well, it turns out we were able to come up with a way to make an adjustment to our declarative flocking model, distributed controller, to what we call distributed MPC with acceleration weighted neighborhooding, to synthesize a controller for high-speed flocking maneuvers. So the idea is that this acceleration weighted neighborhooding exploits imbalance in agent accelerations during a turning maneuver to ensure that actively turning agents are prioritized. So if you're an agent and you're trying to figure out your next acceleration based on your neighbor's speed and position, right, then you might want to see, oh, so I have some agents that are accelerating quite a bit. I can approximate a calculation of the acceleration of my neighbors by looking at their velocities over the past 2 time steps, right? And using that to approximate their accelerations. So these highly accelerating neighbors must be up to something. Let me follow their suit. I'll give them greater preference in priority in computing my next velocity. And so again, we have, like in nature, we only have a few initiators that are aware of the turning maneuver. And this approach that I just outlined ensures that this local information is propagated throughout the flock in a scale-free manner. So what does it look like mathematically? So that we modify our cost function. You remember J sub I hope, at time t for agent i's cost function. Here you have the separation term and the cohesion term. And then we add a velocity matching term. So this is, again, looking at the Euclidean norm of the difference between agent I and agent J's velocity, right? And J is one of the neighbors of I at time t. But now it's not just a normal velocity matching term where you're trying to minimize the, the difference between velocities of agents. It's a weighted sum over your neighbors. And the weight gamma sub ij is going to prioritize or give preferential weight to those neighbors that are most recently highly accelerating. And that's what this, it's kind of a softmax formulation. And that's what it's doing. So this delta Vj of k is an approximation, a good approximation to agent neighbor J's acceleration at time k, which is at where this is being evaluated. And so it's a normalized preferential weight term. And this term, this gamma here is used, it's a large constant used to stabilize the softmax function, because without it, this term would be less than 1. So we use gamma appropriately to scale it as needed. And this works. So I hope everyone gets the basic idea. So here are some snapshots of simulation results. Actually, let me start with the middle one, which is not a simulation result. Again, Adanasi and her collaborators have a 2015 paper in which they have, this is taken from their paper, and this is showing a flock of 176 starlings that they filmed, and they carefully tracked each of these 176 starlings' trajectories, and you can see this beautiful, I forget the term that you use in 3D, but this kind of beautiful, I wish I could remember the term. If someone knows the term, let me know what this geometric shape is. But anyway, you can see this shape, and there were only, I think, only a handful of initiators that initiated this high-speed turn. These starlings are traveling up to 40 miles per hour when they make this turn. So it's quite an amazing phenomenon, and we're doing our best to mimic it. So in our case, obviously, we're not at this, what I'm showing you is not 176 agents. This is 20 agents making a 170-degree turn and 4 initiators. And these are their initial positions, and they succeed in making a 170-degree turn. I'll show you a video of that. Now, if you take out our AWN velocity matching term that I showed you before, this one on the right, you just get that the 4 initiators break off from the rest of the flock. So this just illustrates how crucial AWN is in the velocity matching term that incorporates AWN is in executing high-speed turning maneuvers initiated by a small number of agents. Here's the video I promised. So the initiators are in blue. The rest of the agents, the other 11 agents, are in red. And the initiators now take the inside lane, and they initiated the turn. The others are following suit in this linear fashion. There's some trajectory crossing that you can see there. The initiators are no longer on the inside lane. They've nested nicely within sort of the middle of this flock. So that ends the high-speed flocking maneuvers part of my talk. What time do I have? Yeah, I have to just show you some recent experimental results, and then I'll conclude. So we wanted to experiment with real hardware and real drone hardware, and we settled on, and it turned out to be a good choice. I have a picture of it later on. It's a drone called a Crazy Fly, and some of you may have heard of it, I'm not sure, but I'll show you a picture of it. And it's a pretty small, lightweight drone, not too expensive. And so we had to come up with a way to use our technique, our MPC-based technique or declarative flocking technique to produce a controller for this hardware. So I'm showing you graphically, and this is work that is more recent work being led by Andreas from Technical University of Vienna. He's one of Professor Gross's students. And so we have this a swarm or flocking controller for drone I, and you can see its neighbors here. So what are the inputs to this controller? You have, like before in declarative flocking, the positions and velocities, or just actually he just needs the positions of the neighboring drones. And then the drone state of the drone I itself comes into the swarm controller, and it'll do a calculation to produce not a next velocity, but the output of this controller, or an acceleration, but the output of this controller is a position XY. And the reason it's no longer an acceleration, but a position, is because this controller, this inner loop controller, is communicating its set point to I shouldn't call it an inner loop controller. The swarm controller is communicating a set point to an inner loop low-level controller of drone I that directly interacts with the hardware. And it wants a set point to move the drone to in the next period of time. And it's obviously in 3D, so it has to worry about attitude and yaw and hovering controller and all of that. So the green box isn't super important. More interesting is how does the swarm controller or flocking controller compute the next set point? And it uses what we call distributed SPC, which is spatial predictive control for flocking. So it's not model predictive control anymore, it's spatial predictive control. So this flocking controller is trying to produce the next set point based on what's going to optimize a flocking cost function. So it looks ahead, and it has a spatial look ahead. Now it looks ahead at a look ahead distance epsilon for a look ahead prediction horizon of search steps n, capital N. And it will evaluate the flocking cost function C at each of these new positions. But of course, we want to try and minimize the cost function. So we want to look at not the cost function itself, but the gradient of the cost function with respect to the current position PI of drone I. And this will move us towards, hopefully move us in a direction of minimizing the cost function. So we have to do that as well. And then, this is like a weighted look ahead by current look ahead step N divided by the total number of look ahead steps, capital N. So then we have these potential next positions, each of which is trying to, minimize the cost function with respect to the position. And so we compute this next set point that will give the inner loop controller a piece of B by finding the best position in this set of positions Q of PI, the current position, by doing an argmin computation. And we get PS as the best next position. And we provide that as the set point for the inner loop controller. And this works. How do I know it works? I have a quick video that Andreas produced. So let me jump ahead. This is us in simulation, and it just shows that the drones using this controller are able to safely navigate around an obstacle. Not sure why it's taking, yeah, there it goes. It's safely, the flock is safely navigating around that tubular obstacle. The next slide is a little bit more interesting. This is in Andreas's lab, and he's running this controller on. This is the crazy flies. He commanded them to lift off, and now they're running the flocking controllers. Now he's going to command them to move left and move right, which they do from these external commands, but still maintaining the flocking formation inside his lab. And then they're going to just drop to the floor when the simulation, not the simulation, when the mission is over, so to speak. I just like the ending. That's why I kept it for the whole time. So let's see, how am I doing on time? I just want to spend a couple of moments on something that's a little bit different. It's what I call a modular net for Reynolds model. So we all know about neural networks and all of that, but how about, you know, different ways of programming neural networks or combining them? So this is something I call modular net based on, there was a programming language called Modular, invented by Jack Dennis in the 70s and then followed by Arvine at MIT in the 80s. And it reminds me of these data flow diagrams of modular. So we kind of have a data flow diagram, except these are either functions in these boxes, or they could be neural nets. But for Reynolds model, what we have is, you know, this is the cohesion term that I showed you before, and we have 7 neighbors. So current position is x1 hat, x2 hat for the 7 neighbors of the current agent, and this is the controller, the Reynolds model controller given as this modular neural network, if you will. And you take the sum just to mimic what's going on in, so you already have the differences between agent positions coming in. So you have them coming in, and then you're taking x divided by x squared, which mimics this term or calculates this term. And then you have these differences, you're summing them up, which is calculating this term. And then we're not considering, for the sake of simplicity, the velocity matching term. So so these get summed up, and then you have a separation weight and normalized, and a cohesion weight normalized to get the final acceleration. So it's just this modular net representation of Reynolds model. So the question is, how would you train such a thing? So one thing you can do is supply functions for all of the blocks, because all of these blocks are, you know, we know how to compute them. We can just supply functions, not worry about neural nets. And in that case, we would just need to learn the weights, the 3 weights that you see here, WS, WC, and there's a third one, WA. Or you can train each block separately as a DNN and learn the other weights. So you don't, you know, think of another example where you don't exactly know the function. So you might want to train these blocks separately each as a DNN and learn the other weights as well. If there's symmetry in the model, which in our case there is, a block appears 7 times in our flocking net, right? This block. You train it once and instantiate it the requisite number of times. And here's an example of training this function. Or you can replace all blocks with DNNs and train the entire network at once, as opposed to training them separately. no guarantee the weights for the repeated blocks are the same in this case, but these are all variations on a theme. So that's kind of all I wanted to say about ModularNet. I think it's a very compelling approach to having a modular approach to machine learning. So to conclude, what I've talked about is declarative flocking, which is an optimal control framework for the flocking problem based on cost function minimization. We've looked at both centralized and distributed versions of that. We've extended declarative flocking to various control objectives, such as obstacle avoidance and predator avoidance. I've showed you how we learned a distributed symmetric neural controller that exhibited real-time flocking behavior and generalization. We looked at high-speed flocking maneuvers based on distributed MPC plus acceleration weighted neighborhooding. And we've considered an experimental validation using spatial predictive control and crazy fly drones. Ongoing and future work, we're actually collaborating with Flavio Fenton and Elizabeth Cherry at Georgia Tech on using WebGL for high-speed, large-scale flocking, as Flavio likes to say, on your phone. Moving outdoors with the crazy flies hardware is a much harder problem because you don't have the localization hardware that you have in a lab. You have to resort to some sort of almost like a GPS calculation that the drones compute among themselves. Collision avoidance can actually be formally established among the agents in the flock using our distributed simplex architecture for runtime assurance. And Professor Rada Grosu, has a kind of neural network that's explainable and biophysical in what he calls liquid time constant neural networks. This stemmed from work we did earlier in like 7 years ago involving, and Rich was involved, involving doing a model checking on a neural circuit in C. elegans, the common roundworm. This is what the crazy fly looks like, only 27 grams and fits in the palm of your hand. And thank you very much. I really appreciate it.
Thank you so much, Dr. Smolka. Let's see if we have any questions from the participants. Do we have any questions from the participants? Feel free to type your questions in the chat, or please unmute your microphones and you can ask your questions. All right. It looks like we don't have any questions. And that was a really wonderful presentation. I thoroughly enjoyed it, and I hope everyone did. And thank you very much for your presentation today. And thank you very much for your time. It was a pleasure having you today.
The pleasure was all mine. Thank you, everyone.
Thank you.
Wait, there's a chat message.
Yeah.
Oh, okay. Thank you, Steve. I appreciate it. All right. Thanks, everyone.
Thank you so much. Bye-bye.
Bye-bye.